morning, everybody. I have the pleasure to welcome you to this talk about automatic plan-wide calibration of water resource recovery facilities. So the first thing that you will maybe think is what it means about automatic plan-wide calibration. So I'm going to start with the basis, the calibration procedure. If you have been working with a model or something similar, probably you will have encountered that for your model, you need to set certain kind of parameters based on an input data that you have and all the interactions that you would like to model between into the model. But sometimes when you would like to produce your outputs, it really doesn't fit well. You always struggle trying to fit the outputs that you have. So you encounter the first issue about the calibration procedure, that is start the calibrating your parameter, tuning your parameters one at a time until you are able to actually produce the outputs that you expected. For that, you probably will use some kind of fitness function or a certain rule of thumb to make sure that you're leading your parameters to the best way. But or also you can try to use a sensitivity analysis to decide which parameters are more relevant for you. But even though this process is still an issue, and you probably will struggle a lot with it, so you can, as I said, start with a manual calibration, turn your parameters yourself. That it's a trial and error process, that it's probably will take you a lot of effort and time to do it, and always probably will not lead you to the best parameter you would like to encounter. Or you can rely on some kind of protocols. There are, for this specific topic, some different protocols that will lead you or allow you to calibrate better, give you some kind of rules. But in the end, this will not give you the best parameters, as I mentioned, just will lead you to one direction that you would like to calibrate your parameters. Or maybe you can use a computer-assisted trial error simulation. For example, a Monte Carlo simulation that will try one and again your parameters by default until it can achieve with the performance of the model. But let's do a small example about how this will be performed. For example, if you have 10 parameters, or you would like to model 10 parameters by 10 values in a discrete range per parameter by yourself or by your computer, you will have this amount of combinations that you will say probably for a computer it's not that much. We have computers that can manage this effort. But if each simulation in your model takes 1 second, you probably will spend 370 years just modeling one at a time each simulation. Then that's not feasible for what you are trying to achieve in the model parameters. So here you can see the issue, the disadvantage of performing the calibration process by all these different methodologies, manual, Monte Carlo, or following a protocol, is that you really need to spend, it's computational heavy. You need to run your model several times without even any clear guidance on how to improve. And also you will at the end just have the final calibration parameters, but when you would like to recalibrate, or in the future probably would like to recalibrate, it will not possible, because you need to start over again without even any guidance, and here you will be again just recalibrating. So it will not be nice just to share your expertise, share your knowledge with the next step of calibration, or even with your colleague, if your colleague will be the one that use your model. Well, I'm not talking about external reports or meetings where you discuss where the parameters don't fit at all. I'm talking about the connections and interaction of the parameters. Will not be nice to actually share that connection, share that. If you increase one parameters and decrease other, maybe the calibration will be better without these reports of meeting. Definitely will be. I'm sure that you will say that. So that's the reason why we create the XNIT methodology. That is a methodology that blends expert system and neuroevolving of augmented topologies to create neural networks. I know that that sounds really, really specific, probably. So I'm going to go into detail one by one at a time. So I'm going to start with the core of the methodology. There is artificial neural networks. You probably heard a lot about it with ChatGPT and all these kind of methodologies, pretty popular. But these neural networks try to just replicate or mimic the similar performance that will have a human brain to perform a specific task, and are built by connections. There are these links and neurons that are the circles, and this kind of connections, how it's connected, will determine how the performance of your task will be made. And this kind of connections and neurons, we call it topology. And the idea is to, with the input data that you have, you will create this neural artificial network to set your parameter that you would like to produce. But probably you will say, okay, but to create this topology is a calibration task itself, so it's not that easy to do it. So this is where neat methodology comes, or neuroevolving of augmented topologies. That basically, if you're familiar with genetic algorithms or a similar methodology, it will create different kind of topologies to determine which of them are fits best to your problem that you would like to solve. In this case, to set the parameters that you would like to produce for your model. And the way that it did it is creating a first generation of random different topologies. Then you test the parameters of each one of them in your model, and with a fitness function, you determine which of them performs better or suits better the parameters you would like to produce. Then, with those best performing topologies, you replicate or reproduce them, and if you are familiar with the genetic algorithms, and create a second generation of topologies. This start the process again, and you decide until you arrive on the end generation, where you are able to say, okay, this is the final methodology, the topology that I would like to produce. So you will say, okay, that sounds really nice, but the methodology that doesn't stop there. It actually have another component that allow you to also make it more flexible for your model, that are the expert system. These expert systems are basically a set of rules that just let you compile all the probability distribution functions, the ranges, or the control segment that you have in your model, and that will be the one that fits the artificial networks that you would like to produce. So with all these components, you have the XNIT methodology that allows you to create artificial networks to set the parameters you would like to encounter. But let's see how it performs for a model. We tested the BSM2 model. Maybe you are familiar with it if you are into wastewater treatment. We tested for 29 parameters that we selected based on the sensitivity analysis of the paper that you can see below. And we use it for calibrate the 34 outputs at the end of the simulation. So this is the overall performance of how we build the model with the probabilistic functions and ranges of all these input parameters that I mentioned, and we implement the methodology to create artificial neural network for the BSM2 model. And here you can see the performance that in overall it's between 80 and 100% approach with a mean absolute error of 0.08. That it's a really, really good performance for this model for the calibration purposes, because we just took a few less stimulation than if we would try to do it manually. But I would like to show you how many generations we spent. We spent 67 generations with 100 individuals. That it's 6,700 simulations. That it's not all these combinations that I probably show for the dummy example. And with this took approximately 2 days, because the interaction between the model just take around 5 minutes to run in my personal computer, so that will not be that good. But this was for a specific case study that was for a dynamic case. We also tried for a static case. We also tried for a dynamics case, with 220,000 parameters, and also performed really well. And this allows us with the final. And I'm sorry, and you will say, okay, but a lot of methodologies are able to actually do the calibration procedure. What is the advantage of using this methodology if take a little bit more time? And there is the recalibration part, that you will also have the artificial neural networks that collects all the connection interactions and set of rules embedded into it. So skills save you computational time for recalibration, and also help you to recalibrate through time. So finally, just for that take-home message, I would like to say that we were able to create a successful automatic calibration procedure that help you with an effective recalibration over time, and it leads toward real-time implementation in digital twins. That means that you can calibrate through time in a real-time way. We are planning to implement this methodology. We're currently implementing this methodology in a bigger model, that is the Eindhoven model. That is a blank white model with different kind of elements and units into it, that it's have more parameters, it's dynamically, and in order to test the performance of this methodology. And finally, the opportunities that came with this for you that are here listening to me, it's the opportunity to test this methodology to calibrate models with numerous parameters, and also try it for recalibration in the current models that you are encountering. Thank you very much for your time, and here are my details if you would like to know more about it.